Now that we have understood how to approach an engineering drawing, it's time to answer the next important question. How do we actually read it? Most beginners think they should start from the top left corner and read every dimension one by one. That approach almost always leads to confusion. Instead, think of an engineering drawing like reading a map. When you first open a map, you don't immediately read every street name. You first identify the major landmarks. Only then do you look at the smaller details. Engineering drawings follow exactly the same principle. We begin with the main view. Everything else supports the main view. Let's see why. Look carefully at the largest view shown on this drawing. This is the principal view of the component. If I were creating this part in SolidWorks, CATIA, Creo, Fusion 360 or Siemens NX, this is the view I would probably study first because it gives me the maximum amount of information in a single glance. Notice how much we can already identify. We can see the large circular boss, identify the long connecting arms, recognize the forked end, and we can also locate several holes and curved profiles. Even without reading dimensions, our brain is beginning to construct a three-dimensional image. This ability is called spatial visualization. It is one of the most valuable skills a design engineer can develop. In interviews, experienced engineers often look for candidates who can mentally visualize a component before opening CAD software. Remember this, CAD software does not create good designers. Good visualization creates good designers. Software is only a tool. Your mind is the real design software. Now you may ask, if this view already shows the component, why do we need so many other views? That's a very logical question. Let's imagine you are holding this component in your hand. If I ask you to describe it using only one photograph, can you show every surface? Can you show every internal hole or hidden pockets? Of course not. One photograph cannot describe a three-dimensional object completely. The same limitation exists in engineering drawing. A single view cannot communicate every feature clearly. That's why engineers create multiple views. Each view answers a different question. One shows the front, another shows the side, another reveals hidden features. Together, they remove ambiguity. Engineering drawings are designed so that two engineers working in different countries can manufacture exactly the same part without ever meeting each other. That is the true power of technical drawings. Many students ask, why does one simple component need so many different views? Here's the answer. One view can never completely describe a three-dimensional object. Imagine trying to explain a car using only one front photograph. Can you see the engine, the seats, the wheels from the side? Of course not. Engineering drawing solves this problem by showing multiple views. Each one reveals something different. One shows the external shape, another shows the side profile, another exposes hidden internal features. Those aren't extra drawings. They are different perspectives of the same component. The more complex the component, the more important these views become. Now engineering drawing suddenly makes much more sense. Now let's move to one of the most powerful tools in engineering drawing, the section view. When students first see a section view, many think it's another component. It isn't. It's the same component viewed differently. Imagine holding a cake. Now imagine cutting it exactly through the middle with a knife. Once you separate the two halves, you can finally see the inside. That's exactly what a section view represents. Instead of showing hidden edges using dozens of dashed lines, the engineer imagines cutting the component along a defined plane. The front half is removed, the remaining half is projected onto the drawing. Suddenly, internal holes, pockets, steps, ribs, and cavities become clearly visible. Notice the diagonal lines covering the cut surfaces. These are called section lines or hatching. These lines don't represent material type in this drawing. They simply indicate where the material has been cut by the imaginary cutting plane. Think about how much cleaner this is than filling the drawing with hidden lines. A section view reduces confusion, improves readability, and helps manufacturing. And inspection teams understand the internal geometry quickly. Whenever you see labels such as section AA, section BB, or section EE, remember that somewhere in another view there is a cutting plane indicating exactly where the imaginary cut has been made. This is one of the most elegant ideas in engineering communication. Now let's look at another important feature, the detail view. As components become more complex, some regions become too small to dimension clearly in the main view. If we try to place every dimension around these tiny features, the drawing would become crowded and difficult to read. Instead, engineers enlarge only the important areas. Think of it as using the zoom function on your mobile phone. You don't enlarge the entire photograph, you zoom into the region that matters. That's exactly what a detail view does. It enlarges a small area so that dimensions, radii, chamfers, grooves, and other fine features can be communicated without confusion. Whenever you see labels like a detail I, J, or detail K, remember that they are simply magnified versions of small portions of the original view. Good engineering drawings are not about fitting everything onto one sheet. They are about communicating information as clearly as possible. We have reached the point where most beginners usually start. But notice something important. We didn't begin with dimensions. We earned the right to read them by first understanding the component. Now every dimension has meaning. Let's begin with the most familiar symbol, the diameter symbol, represented by phi. Whenever you see this symbol, it tells you that the dimension belongs to a circular feature. If a hole is marked as phi 20, it means the diameter of the hole is 20 millimeters or 20 units. Next comes the radius symbol represented by r. Unlike diameter, which describes the entire circle, the radius measures the distance from the center of the circle to its edge. Radius dimensions are commonly used for rounded corners, fillets, or curved transitions, mostly arc-like features. Why are these rounded corners important? Because sharp corners create stress concentration. Round corners help distribute stresses more smoothly and improve the durability of the component. Now look at the angular dimensions. These define the exact orientation of inclined surfaces. Even a small angular error can affect assembly or interfere with the movement of mating components. Every dimension on this drawing answers a specific manufacturing question. How long, how wide, how thick, how far apart, how large, how deep. Dimensions are not random numbers. They are manufacturing instructions. If a dimension is missing, the machinist must guess, and engineering should never depend on guesswork. Now you know how to understand views, sections, and dimensions. But there's one thing even more important than dimensions: precision. In the next video, we will explore GD&T, datums, and how real industries ensure every part fits perfectly. If you are serious about becoming a design engineer, subscribe to the channel, and I will see you in the next lesson.